My name is Nathan Sturtevant, and today I'm going to talk about how we can predict the performance of bidirectional search. There's a long-standing problem, about 50 years old, of when bidirectional search, in particular bidirectional heuristic search, will perform well or outperform unidirectional heuristic search. In this paper, we're going to show how the performance of bidirectional search depends on states that have heuristics that are both low and inaccurate. Now, as I said, this problem is about 50 years old, and there's been recent work in the last 5 years that's tried to readdress this problem. This began with Barker and Korf in 2015. They defined a strong heuristic and some parameters here to make a prediction, which is a fairly accurate prediction, but there's a couple small issues with this. First, the heuristic is defined by its performance solving a particular problem and not the intrinsic properties of the heuristic. And so that's a dependency we'd like to break a little bit. This also had things like assuming that the search was symmetric and that it met in the middle, and so these are not necessarily true as well. In 2017, there was another paper that introduced the algorithm. The algorithm was guaranteed to meet in the middle, so it was really trying to follow up on that previous work. And in this paper, then, there was some different analysis that was based on regions of the state space, showing that if you compared the sizes of the different regions and then looked at the strength of the heuristic, then you might be able to predict which would do better, bidirectional or unidirectional search. This is, again, really good analysis, but it predated actually the theory of bidirectional search. And so, for instance, there's some improvements to that needed to be made, and those were introduced last year. But more directly, this analysis is for and now we have a better understanding of other algorithms for bidirectional search. So it's later in 2017 at ICAPS that there was a paper that introduced for the first time the theory of bidirectional search. And in this talk, we're interested in front-to-end bidirectional search. We're going to assume that the heuristic is admissible, but not necessarily consistent. And this problem corresponds, we'll show in a second, to finding a minimum vertex cover on a bipartite graph. What's important to understand here is that we want to ask for a pair of states, one in the forward direction, one in the backwards direction. Do they need to be expanded? And there's 3 conditions. First, the state in the forward direction must have f cost that's less than c star, where c star is the optimal solution length of the path. The state in the backwards direction similarly must have an f cost which is less than c star. And then third, the g cost of the 2 states together must sum to something that is less than c star. And if you have all 3 of these conditions, in order to guarantee that c star, that the solution is optimal, have cost c star, then we must expand one of either a or b, but not both. So we can write this out as a graph here, where the nodes have their g costs inside them, and next to them is the number of states that have that g cost. All the nodes in the forward direction that would be expanded in a forward unidirectional search by a star are on the left. The ones would be expanded by a backwards unidirectional search by a star on the right. And then we have edges between groups of states. And these edges are saying if the pair, that is the g of f plus g of b, is less than c star, do one of this pair of states have to be expanded? And because there's multiple states sometimes with a given g cost, then we would be choosing between them. So particularly here, we could choose to either do 2 states in the backwards direction with g cost 12, or 1 state in the forward direction with g cost 1. And we can save 1 node expansion by doing the forward search, 1 step, instead of doing the last step of the backwards search. Now, in general, we can choose any meeting point here, and we can get rid of many of these edges to look what's actually going on with node expansions. If we were to meet at this point, for instance, that is we did up to g cost 6 in the forward direction, up to g cost 5 in the backwards direction, and met there, then we could add up the number of node expansions and we'd come up with 148,657. And I'm not going to go for the details, but generally you're going to have a contiguous partition on each side. So if we look at Rubik's Cube, what happens here is we think about, well, I have this choice I could do if I've done a completely forward search. So this is theoretical reasoning. We wouldn't actually do this during search. But we could say I could do a complete forward search, and then I could start asking, is it beneficial to do some backwards search? And we'd say, yes, if I were to have done 1 node in the backwards direction, I'd actually save 3,000 nodes in the forward direction. So that's good. That means that a bidirectional search would be useful. And as we continue, we say, again, 3,000 nodes, 3,000 nodes, 2,000 nodes. And we'll continue to save node expansions by doing this backward search until we actually come up. In this case, the best meeting point is right in the middle here. And just to say, the red states are critical states here, and bidirectional search works well because there are a lot of critical states, and so we save a lot by doing the backward search. Now, we originally were using this tool and these visualizations to try and understand what was going on the pancake puzzle. And when I looked at this problem with the gap heuristic, what we found was that actually there were no critical states in the state space. So these, again, these ones in red are called critical states. And so what we see here is if I start doing backward search, trying to save nodes in the forward direction, there are no nodes in the forward direction to save. And so the backward search is growing. In this case, it's growing exponentially, at least initially. But I'm not getting any gains in the backwards direction by eliminating nodes that would have been expanded. So all of this is work that I do in the backwards direction, and I actually get no savings at all during the search. So what is going on here? Well, we want to look at these critical states, and we want to ask the question, why do these critical states appear? When do they appear? And can we predict whether they're going to appear? I can't go through all the details here, but I'm going to give a high-level overview. Again, the details are in the paper. So one thing we could do is we could, and sorry, let me just say here that these states, in order to be critical states here, they have to have large G cost because that puts them sort of at the bottom left-hand corner of this graph. And then the other thing is that their heuristics, if their heuristics are perfect, then they won't have F less than C star. So they have to have large G cost, but they have to have very small H cost in order to show up in the graph. So we're going to do a couple things. We could look at states near the goal, and we could say states near the goal, we know they actually have large G cost, do they have low H cost? And if we look, for instance, in a grid pathfinding domain, what we would see here is the states near the goal with something like a straight line heuristic would be actually having very accurate heuristics, and so we would not see critical states from this area near the goal. But in other domains we might. We could also sample states that have low heuristic values anywhere in the state space. And again, in something like this with a straight line heuristic, these are going to be states within this circle. And we can find here that there are some states, the ones in orange here, that do have low heuristic values. And so these also have the potential to be critical states. But states with high heuristic values, no matter where they are in the state space, really don't have a potential to be critical states because the heuristic will prevent them from being part of this vertex cover. So we see that it is possible to measure whether we have critical states, and measuring that is going to be helpful in predicting whether bidirectional search is going to work well. We do notice, and by these predictions, we wouldn't expect bidirectional search to work well in grid maps. But there's a third thing, which is this assumption that the state space is symmetric, which doesn't necessarily hold. And we can see here an example where a forward search in red does much less work than a backward search in blue. And when we have asymmetry, this is another case where a bidirectional search can outperform a unidirectional search. And so in grid problems, actually the two searches are fairly close in performance, and asymmetry is one of the dominant reasons why. Let's look at another domain here. We're going to look at two more examples. So let's look at Towers of Hanoi with a pattern database heuristic. So here we're going to have two heuristics, one that has tiles or disks 4 to 7, and one has disks 1 to 3. And we apply the abstraction that looks at disks 4 to 7. We see here on the right-hand side that it looks like it's only going to take one move to get this state to the goal state. But when we look at the actual problem state, we're going to see that we're actually quite far from the goal, because we have to unload disks 1, 2, and 3 before we can get 4 on. That means that there's many combinations that this could happen. So there are many low states with low heuristic values that are actually very inaccurate. And so this is an example domain where our experimental results show that bidirectional heuristic search can outperform unidirectional heuristic search. The other case I'm going to look at quickly is uninformed search. Well, here the heuristics are low everywhere because there's 0. And for most states, they're inaccurate. And so we expect to see in uninformed search, which is something we've sort of always known, is that in uninformed search, we expect the bidirectional search to outperform the unidirectional search. So in conclusion, critical states are what we need to be looking at to understand when bidirectional search will work well or not work well. These are states with both low and inaccurate heuristics. And the more critical states there are, the better bidirectional search will perform. Please take a look at the paper if you'd like more details. Thank you.